In this last example, in our introductory part of the course, we're going to look at a partial differential equation. Partial differential equations are so called because they contain partial derivatives, and that's because they feature multiple independent variables. So, for instance, suppose you want to describe the amplitudes, the vibrations of a guitar string, and we'll look in particular at small amplitude vibrations for simplicity. Well, the vibrations, of course, vary with time. They happen in time, so you're going to need a time variable to describe them. And displacements of the string vary along its length, so you also need a spatial variable to describe that. In this case, we're going to use x to describe horizontal displacement along the string, or displacement along the length of the string, if you like. And we will use y as a sort of a transverse coordinate to describe the amplitude of the oscillation of the string. We're going to assume that the string only has transverse oscillations. There are no oscillations along the length of the string. And that means that the tension is going to be uniform along the length of the string. The net force, the net horizontal force, or the net longitudinal force, I should say, along any chunk of string like this is going to be zero. So the tensions at both ends will be exactly the same. We'll say that the mass per unit length of the string is represented by rho. We need to know that because we're going to have to apply Newton's law. So what does Newton's law say? It says F equals ma, or in other words, F equals the mass. So I've drawn here a length of the string a piece of string of length delta x, because it stretches from x minus delta x over 2 to x plus delta x over 2. So its length is delta x, therefore its mass is rho times delta x. Rho times delta x, therefore multiplied by the acceleration of the string, and again we're only considering transverse motions, so the acceleration of the string is going to be the second derivative of y with respect to time. That's ma, if you like. The mass of our little chunk of string, our little length of string, rho delta x, times its acceleration in the transverse direction, d2y by dt squared. That has to be equal to the net force in the positive y direction by Newton's law. So what's that going to be? Well, we just have to look at the transverse forces on both ends of our little piece of string. So on this right-hand end, it's going to be the uniform tension T times the sine of this angle theta 1. So we're going to get T sine theta 1 minus the tension on the left-hand side, which will be minus T sine theta 2. Okay. Now, last time we had a tangent of an angle like this come up, and we were able to say, well, that's just dy by dx. Okay. These sines are going to be approximately equal to the tangents of the same angles if we're dealing only with small amplitude oscillations. So if these angles theta 1 and theta 2 are small, we can say that they're approximately, the sine theta 1 is approximately tan theta 1, and sine theta 2 is approximately tan theta 2. Because again, we're talking about small amplitude oscillations. So that means that we can write the tangents of these angles as dy by dx. Although in this case, because there are two independent variables, x and t, those are going to be partial derivatives. So we have di y by di x, evaluated x minus, at x, I think that should be x plus delta x over 2 minus t di y by di x at x minus delta x over 2. Now, we've done this for a delta x. Suppose we let that become an infinitesimal dx. And here we've essentially got the difference between two values of di y by di x at points separated by a distance delta x. If we divide that by delta x and let delta x go to 0, we're taking the derivative of that quantity, so we're going to get a second derivative of dy by dx on the right-hand side. So what we'll end up with is rho times di 2y by di t squared. I should have been writing that as a partial derivative. Equals t times di ty by di x squared. Or, in other words, di 2y by di t squared equals t over rho times di 2y by di x squared. This is called the wave equation. And it comes up in various contexts, not only when you're modeling vibrating strings. In fact, it's even somewhat similar to the Schrödinger wave equation of quantum mechanics. And that's what we've just derived, essentially. We've shown that this equation models small amplitude transverse oscillations of a string that is fixed. It's going to be fixed at two ends. That's what we're going to say when we impose some boundary conditions. As the name suggests, some of the solutions of this equation are going to describe waves. That's one way that the string can vibrate, by having waves travel along it. So in particular, it's easy to check that these functions, y equals a sine k times x minus the square root of t over rho times t, these are solutions of this equation. And this represents a wave of amplitude a traveling in the positive x direction with speed square root of t over rho and angular frequency k, where k is just a constant, times root t over rho. Now this frequency, this angular frequency of k times the square root of t over rho becomes more interesting when you apply boundary conditions that say that the ends of the string are fixed. Let's bring in some such boundary conditions. So let's say that one end of the string is where x equals 0. So we'll say that y of 0t equals y of capital LT, the other end of the string being where x equals capital L. And let's say that both of those have to be 0 for all t. That simply means that the ends of the string are fixed. This string of length capital L. What do we get in that case? These boundary conditions are satisfied by, among other functions, solutions like this. And here I'm just adding two solutions of the form we've already looked at. So I'll call one A plus times sine k x minus the square root of t over rho t. So that is like the solution we just saw. And then I'll add to it a solution that's really of the same form, except in that case I will write it as k sine k times x plus the square root of t over rho t. So these represent two waves traveling in opposite directions. And by superimposing these two solutions of the original partial differential equation, we'll be able to satisfy these boundary conditions. To see how we do that, let's apply the first boundary condition, namely for x equals 0. Well, if we set x equal to 0, this is just going to be a plus sine k minus t over rho, the square root of t over rho t. And this will be a minus sine k times plus the square root of t over rho t. Well, the sine of k times minus the square root of t over rho t is just the same thing as minus the sine of k times the square root of t over rho t. So these will equal 0, as they have to according to the first boundary condition, if and only if we set a plus equal to a minus. So the two waves traveling in opposite directions have to have equal amplitudes. What if we apply the second boundary condition? That which applies when x equals L, namely at the other end of the string. Then we have that a, well, let's say a plus, even though a plus will have to be the same as a minus, a plus sine k L minus the square root of t over rho little t, plus a minus times the sine of k times L plus the square root of t over rho t equals 0 for all t. Well, if that is going to be 0 for all t, then, well, we know that these two amplitudes are the same, but these terms are going to have to cancel out. Okay. And that means that k times L is going to have to be a multiple of pi. In other words, because both ends of the string are fixed, k can only have certain values if we are to satisfy our equation. So in particular, k must be plus or minus n pi over L, where n is 0 1 to any non-negative integer. So these solutions will be familiar to people who play stringed instruments. This means that the waves can only have certain frequencies. Namely, those frequencies are k, which is n pi over L, times the square root of t over rho, divided by 2 pi, if we're finding the frequencies as opposed to angular frequencies. So that gives us n over L times the square root of t over rho. So the lowest non-zero frequency, which corresponds to n equals 1, is what is generally called the fundamental frequency. This is what is normally called the fundamental frequency. That's the frequency to which you tune the string when you're tuning an instrument, for instance. And then the strings, the frequencies that correspond to higher values of n are what are called the harmonics. These, of course, alter the characteristics of the sound. Now, this equation, the equation is linear. We'll talk about linearity in more detail later. And this implies that any linear combination of solutions is itself a solution. So you can take any superposition of the fundamental frequency and any harmonics you like, and you'll still get a solution. So the sound can include, the fundamental, or it doesn't have to, but it can include the fundamental and any combination of the harmonics. In principle, all of the tones that you get from the string will be either the fundamental or some multiple of the fundamental frequency. This expression, our expression, also tells you a little bit about, tuning instruments. There are these different factors that come in. Of course, the length is a factor. The greater the length L, the lower is going to be the pitch, the fundamental frequency. But the higher the tension, the higher will be the frequency. And then again, the higher the mass per unit length of the string, the lower the pitch is going to be. So this is why musical strings that are meant to give you low notes are often wound with wire and that sort of thing to give you a higher density. And that can all be worked out as we've just done it by sort of deriving a partial differential equation and considering the solutions. Now, that was just an example to show you a partial differential equation, so you have some idea what they look like and how they might arise. This course will not cover PDEs. If you go on to take a course in scientific computing, it's pretty likely you'll look at numerical solution of partial differential equations. But this course will focus on so-called ordinary differential equations. And Ordinary differential equations are those that just contain total derivatives, ordinary total derivatives, because there's only one independent variable. So we've looked at a number of examples of differential equations. We've seen how they can arise in different contexts. We've learned a little bit about their solution. From now on, in the next chapter of the course, we're going to focus on this class of linear ordinary differential equations with constant coefficients. And again, that's the only really broad class for which there are systematic ways of solution. And that will be the topic for next week. So in the upcoming live meetings, I can handle any questions or comments you might have, and maybe we'll look at some further examples of differential equations in a somewhat general sense. Then next week we'll go on to look at linear ODEs with constant coefficients. See you next time.